Today we're starting a new chapter. It's called Exponential and Logarithmic Equations or Functions. This is an exponential function. So when we talk about an exponential function, it's of this form. F of x is equal to b raised to the x, where b is greater than 0, b is not equal to 1. We call that the exponential function. Now, this is what the exponential function looks like when you graph it. So imagine you have a graph that looks like this. What is constant about every one of these b to the x graphs is that they go through the point 0, 1. Now, that can change when we change the form of the equation. But right now, for now, you're going to assume that it goes through 0, 1. So for y is equal to b to the x, we have a horizontal asymptote as x goes to infinity. Okay. And then that is only if the b value is greater than 1. So when the b value is less than 1, we have y is equal to b to the x. Where b is less than 1, you have a graph that looks like this. It starts big and then goes through 0, 1, and then uses the x-axis as its asymptote as we go from left to right. Now, the domain for each of these is negative infinity to positive infinity. Okay? Now, notice the blue graph slants downward, right? I want you to also recognize that the number is greater than 0, but less than 1. So any fraction causes that to happen. Now, let's make sure that we identify the horizontal asymptote for all of these. The horizontal asymptote for these are y is equal to 0. There is no vertical asymptote, and the function is continuous. For all x. Okay. The function is also 1 to 1. So now let's imagine that we have to go and sketch a graph. Okay, so we're going to sketch the function y is equal to x and y is equal to 1/2 x. So these are our two graphs. Now, here is what happens. When you basically graph this, you're going to graph it like so. You're going to take the graph y is equal to 2 to the x, and what you're going to do is you're literally going to give me the x and y coordinates for the values from 1, 2, and 3 to -1, 2, and 3. And you'll notice that -3 is actually 1/8. Then -2 is 1/4. -1 is 1/2. Then we have 1. Then we have 2. Then we have 4. And then we have 8. Let's go and plot all those points on our graph. And those are our basic points. And when we graph, it looks something like this. Now, when you go and take the rest of these points for y is equal to 1/2 x, you'll find that for y is equal to 2 to the x, y is equal to 1/2 of x looks very similar to this. Y is equal to 2, but it happens to be reflected in the y-axis. And you end up with a graph in blue that looks like this. Now, the reason why it's a reflection in the y-axis is because of some deft little mathematics. So let's say we had y is equal to 1/2 to the x. So that is the same as saying 2 to the negative 1 raised to the x, isn't it? Now, when you do that, you have a power of a power, which really means y is equal to 2 to the negative x. Now, that negative that is here actually says that this is a reflection in the y-axis. And we had studied that in past units. So essentially 1/2 to the x is the same as 2 to the negative x, which is just a reflection of this equation here. So we can just mirror the points around the x-axis. And now let's talk about the transformations that could possibly happen with this function. So for this, we're going to have to get really serious. I'm going to use a lot of space here. So for y is equal to 2 to the x plus 3, this is really a horizontal translation left. Now remember, this one up here was our original equation. Y is equal to 2 to the x. So when we go and change our equation to be just shifted left and right, we can go and look at other forms of the graph. So imagine I have a function that looks like this. 2. Y is equal to 2 to the exponent x minus 3. And just for fun, what we'll do is we'll add a vertical stretch. So imagine we have 4 times the quantity, 2 to the x plus 3, and then we take 1 away. So the 4 we recognized as a vertical stretch factor 2. This part here tells us that we have a horizontal that's a Z, horizontal shift. Let's go right 3. And this last one, I'm going to make it purple. This last one tells this is a vertical shift down 1. And we're done. That's it for our transformations. There's not much that we have to do other than use our common sense to do these. All right, so now let's go and take a look at this set of problems here. So let's say I give you a problem where I say find the exponential function f of x is equal to b to the exponent x such that the graph is going to pass through the given point. So for A, let's say our point is -1 and 5. All right, so if it's -1 and 5, here is your solution. Your solution is given by 5 is equal to b raised to the -1. So you know that b raised to the -1 really means 1 divided by b is equal to 5. So now what we have to do with this problem is solve for b. And in this case, you solve for b by flipping everything and solving for b, and you end up with b is equal to 1 over 5. So therefore, the equation is f of x is equal to 1 over 5 raised to the x, and we're done. Let's say I have another problem, b, and it's the point 2e. E is what we call the natural number. It's approximately 2.71, and it goes on forever. It's a transcendental number, very similar to pi, okay? So you just need to be able to recognize that that is a basic number, okay? So when you go and solve for this, here is your solution. You say, okay, e is equal to b raised to the x, but x is in this case 2. So now, in order to get b by itself, we have to take b and raise it to the 1/2. So we got b squared raised to the 1/2 and e raised to the 1/2, which gives us e to the 1/2 is equal to b, because of the cancellation of power of a power on b squared raised to the 1/2. So now there we have our answer for b. So there is b, and now we just restate our equation. So therefore, f of x is equal to b is e to the 1/2 all raised to the x. And then you can simplify that to be e to the x over 2. And that is our final answer for f at x. All right, so now let's move on to the next question. All right, suppose that I have a function given as f of x is equal to 2 to the x minus 6 plus 2 to the x to the 3 minus x divided by x plus 2. And I've asked you to find the x and y intercepts. So how are you going to do that? So here is our solution. So for the y-intercept, we let x equal 0. So we end up with f of 0 is equal to. So we have this solution here. 2 raised to 0 minus 6 plus 2 raised to the 3 minus 0. 2 to the 0 is going to equal 1 minus, well, 6 plus, oh, that's supposed to be a 0. And then 3 minus 0 is 3. So 2 to the 3 gives us 8. All right. So now we divide by. Now remember the base of that problem. We had to replace everything with a 0. So this x on the bottom of our problem here really should be 0 plus 2. So 0 plus 2 is 2. So now let's simplify the top half of our problem. We have 1 minus 6 plus 8. So negative 5 plus 8 is going to be 3 over 2. So that is f at 0. So the y-intercept is, well, 0, 3/2. And we'll just put a box around this to kind of identify it. Now we have to find x-intercepts. So for the x-intercepts, we let y equals 0 for the x-intercepts. So in doing so, you're going to get the following. 0 is equal to 2 to the x minus 6 plus 2 to the 3 minus x all over x plus 2. Now, the only thing that makes this whole thing equal to 0 is literally the top half of our equation. So we can just ignore the bottom half. So we end up with this for our solution. 0 is equal to 2 to the x plus 2 to the 3 minus x, and then the minus 6 is somewhere in there. So let's put that in. Minus 6 plus 2 to the 3 minus x. Okay, so now let's go and solve. So when you have that, we want to think of this as our original equation looking like this. 2 to the x minus 6 plus 2 to the 3 divided by 2 to the x all equals 0. All right? Now, what we can do to make our lives easy is to make a common denominator of 2 to the x for everything here. So literally what we can do is have 2 to the x over 2 to the x multiplied by each of these things here. 2 to the x all over 2 to the x. So when you multiply those out, you're going to get, well, 2 to the x and 2 to the x on top of this part here becomes the following. 2 to the 2x, isn't it? Minus 6 times 2 to the x plus, well, 2 to the 3. And then everything here is actually all over 2 to the x. And all of that is equal to 0. Now that I have that, what we can do is we can pull out a power of 2 from this one here. So when we do so, it saves us some time. Also, remember, because we only care about what makes this thing equal to 0, this is the only thing we care about. So what we have is a reworking of this problem in such a way that you have this problem here. So your solution is going to be 0 is equal to 2 to the x, but then it's raised to the power of 2, minus 6 times 2 to the x plus 2 to the 3, which is really nothing more than the value of 8. Now, if you're having issues with this, I could factor this right away, but I want you to imagine that this was a squared minus 6a plus 8. And all you had to do was factor this. So if you factored this, if you factored the right side of our problem, we'd have two brackets here, wouldn't we? And we'd have to look for two numbers that multiply to 8 and add to -6. Okay? So two numbers that multiply to 8 and add to -6. And what you're going to do is you're going to find out that you have -4 and -2 as our factors that work for us. And then all we have to do is put down our a value, but our a value is actually 2 to the x. So we'd write 2 to the x minus 4 and 2 to the x minus 2. So now what that tells us is this. It tells us that our information is set up in such a way that we're going to have to basically account for two possibilities. 2 to the x minus 4 is equal to 0, or we have 2 to the x minus 2 is equal to 0. And all we have to do is solve. And we have 2 to the x is equal to 2. So this really means 2 to the 1, which really means x is equal to 1. So we just drop it. So for this other one, we have 4 and 2 to the x. Now, all you have to do is change 4 into some power of 2. So 2 squared is equal to 4. So 2 to the x is equal to 2 squared, which really means x is equal to 2. And there is our final answer. So what we just found here, let's go back. We did all of this for one reason and one reason only. We needed to make sure that when we did this problem, we started out by looking for the X-intercepts, right? We were looking for the X-intercepts. We let our y's equal to 0. We got rid of the denominator because it meant nothing when we were trying to find our values. Then we rewrote this part to give us this, x cubed over 2 to the x. Then we came up with a fraction in the form of something over 2 to the x by multiplying the top and bottom of each of the other terms by 2 to the x. And then we focused in again on the numerator. Now after we focused in on the numerator, this gave us this quadratic in the form of 2 to the x. And all we had to do was imagine that the 2 to the x was like a variable a. And we knew that all we had to do was find two numbers that multiplied to 8 and added to -6. So then we got this factorization to the x minus 4 and that. And then in order to find our x values, all we had to do was bring our stuff over to the left side and then simply make each of the terms on the left side be a power of 2. Those matching power of 2s allowed us to drop our x values, drop our base values of 2 to get x is 2 and x is 1. So therefore, the x-intercepts are, well, 2, 0, and 1, 0. And we're done. All right. So now what I'd like you to do is I'd like you to do these specific questions. You're going to work on page 295, number 13 to 27, and you're going to do the odd numbers until the end of class today. Good luck.